Thank you very much. Hi everyone. Thank you for coming. And in the next 30 minutes, I'll tell you a story of my first introduction into the world of cybersecurity, although I'm not a cybersecurity engineer or not related to security at all. And I'll talk about a story of how I was able to reproduce a publicly disclosed vulnerability on Raspberry Pis. And I'll also talk about Bluetooth itself, the vulnerability itself, and why patching the code for the vulnerability isn't necessarily enough. But few words about myself. So I came to UK 11 years ago to study. I studied computer science in Oxford Brookes University. Successfully graduated in 2019. Since then, I've been working. I started working as a full stack engineer and then backend engineer. But 5 years ago, I made the decision that one of my friends called a masochist decision, jokingly, of course, and transitioned to embedded engineer. So since then, I've been working as an embedded engineer. And in free time, I also write about digital privacy and tech policy. The ironic thing about all this is that I actually hated programming in school, and I didn't expect that I'll be working in IT. Yet here I am, giving my second presentation in 6 months, and in my second B-Sides ever. One disclaimer as well. I do not recommend anyone trying to exploit the vulnerability that I'm going to discuss in public or without any consent. So if you want to try it out yourself, please do this in your own test environment or with your own devices. Although, to be honest, if someone uses a speaker with a very loud music, you can do it. So, Bluetooth. Before we start, can please raise your hand if you use Bluetooth on a regular basis, whether it's for work purposes or not? Wow, so basically, well, there's half of them, so basically amount of people who voted Labour later in previous general election. So, Bluetooth protocol. It is everywhere around us. More and more devices support communication over Bluetooth, and for protocol that has why it became so popular. This protocol was named after Howard Bluetooth, a Danish king who was able to unite lands in Denmark in 10th century, if I remember correctly. And this protocol was designed as a way to communicate between devices and exchange data with each other. And eventually it progressed. So basically, first device was a wireless mobile headset, but then it evolutionized, and it's being used in smartphones, EVs, or smartphones on wheels, as I call it, in IoT, including this shit Bluetooth fork. I don't know who else designed, but anyway. And to understand the scope of how many devices are, the official organization that is responsible for designing Bluetooth protocol reported that in 2023 over 5 billion devices were shipped. So, yeah, the scope is enormous and sometimes difficult to understate. So let's look at the specifics. Now, this is the Bluetooth protocol stack. And if that if that arrows and abbreviations, squares, circles frighten you, I'll explain to you as if with the TCP/IP version. So we have Bluetooth consists of host and controller. Controller is basically the physical and data link layer parts of the TCP/IP, which are responsible for maintaining and establishing connection between two devices or more devices, since Bluetooth allows to communicate one central to multiple peripherals. And meanwhile, the host is responsible for application-specific data. So basically, create data that you want to send to another device, and then controller proceeds to send it over the radio. In this talk, we'll focus on three elements of this stack, which are part of the host control interface, which act as a bridge between host and the controller. So basically, those are CSO, ACL, and link manager. Don't worry. Just remember those definitions. We'll get to them later. So there is a joke that usually the IoT S in IoT stands for security, and with Bluetooth, ironically, it's also the same because over 25 years since Bluetooth protocol existed, almost 1,000 CVEs were filed. Whether it's for protocol or the stack implementation, and one of them was Braktooth. So in August 2021, a group of researchers from Singapore discovered 16 vulnerabilities in the protocol stack definitions in the commercial vendors such as Intel, Qualcomm, Espressif, and Cypress, which allows to exploit the communication between two devices with a different range, starting from basically doing denial of service against the connection, disrupting it, to at some with Espressif even going for arbitrary code execution. And because of such big names among those vulnerable, it meant that billions of devices were vulnerable to this. The researchers didn't test Raspberry Pi though, and at work I work with Raspberry Pi, so. I reached out to them and asked for a proof of concept because at that time, they haven't published yet. And, they've been gracious enough to provide the POC so that I can test it on Raspberry Pis. So I immediately set up the, test system, which is basically, I use Raspberry Pi, as a central. I use a speaker as a peripheral device. In my case, it was a DVM speaker. Actually, a really good one. I recommend that. And meanwhile, I act as an imposter trying to attack the communication between between devices using the hardware. In this case, it's ESP32 rootkit, obviously from my laptop. But to be honest, the researchers though said that it's explicitly this one, but actually you can replace it with the regular ESP32 microcontroller that supports Bluetooth. But just make sure that you use ESP proc. That's due to the requirements for the proof of concept. So this is how it looked like in real life. So you have Raspberry Pi that's connected to the power bank. There's a speaker, and there's my ESP32 rootkit. So, first things first, I needed to set up the connection between Raspberry Pi and the room speaker. At that time, the Raspberry Pi was running Ubuntu 20.4 LTS with latest updates, including security updates. And if you're surprised by seeing command line, the reason why is that my Raspberry Pi was running a headless, basically UI-less version of the Ubuntu, so due to my work purposes. However, it will also be helpful to show exactly what's happening behind the curtain. So basically, establishing connection has been pretty straightforward. I used the pin code to connect, so I verified the pin code. And if you can see, it says Timebox Evo Audio, meaning that the device has been paired, connected, and it's ready to communicate with the Raspberry Pi. So, my first attempt was using the vulnerability called invalid timing accuracy. Now remember the abbreviations that I mentioned previously, SEO, ACL, and Link Manager. So we'll focus on Link Manager here. Link Manager protocol is a part of the Bluetooth controller that is responsible for establishing and managing pairing and managing and pairing and authentication of the pairing between two devices, and then keeping them in communication between each other. In order to maintain the communication, it uses the timing request. Basically, it uses timing request response exchange. So basically, the central device, which is Raspberry Pi, sends regularly the timing request messages, and the device should reply with a response, meaning, and then Raspberry Pi says, okay, so it's live, it's ready to receive data, so all is good. What exploit does is that if you send the malformed so if you send a malformed packet towards the master, so towards the central device, it will stop. So basically, it will stop. It will ignore that. It will ignore that packet and basically throw it away, essentially causing the disruption of the communication between two devices. My attempt at running this did not work out, so the devices still remained connected. But ironically, then when I reached out to the researchers, turned out it was actually a bug in the POC. So nothing was wasted. It's not all was wasted. So then I moved to the second attempt at exploiting it, which is involved the max slot type. So there are 5 types of the logical transport protocols in Bluetooth, depending on whether the central device connects with multiple peripherals or just one peripheral. To communicate with only single peripheral, it uses either SCO or ACL. ACL stands for asynchronous connectionless, meaning that so in this protocol you send in this case you need to send a lot of messages, and you only care about a high bandwidth of the communication, and you don't care about the response from the device. So, for example, it is used when you communicate your device to a speaker and you want to play music on it. SCO, on the other hand, is actually used for timing synchronization. Basically, for example, when you need to use you use a wireless microphone, because with them timing is very important. With ACL, it's not that important. One of the fields of the ACL is the logical transport address. So basically, what this exploit malforms. So basically, that exploit crafts the packet by producing the LT address at all zeros. The problem is, for communicating with one device, you can't do that, and because it's been reserved for the active peripheral broadcast when one central device connects to multiple peripheral devices. And theoretically, in any other case, what firmware should do is it should detect an exception and basically discard that packet. The problem is, the Cypress and Broadcom SDKs doesn't do that. So basically, it receives a message that says, "Oh, I don't know what's happening, so I'm just crashing." So that's me. So basically, here's my attempt to run the second exploit. So these logs are pretty much what I expected. Then I saw this and I get hopeful, because if you notice the line agent unregistered, so on Linux devices, the main Bluetooth stack is called Blues, and agent object is responsible for establishing and managing pairing and the connection authorization between two devices on an operating system level, to make sure, so basically to save that data. And when it says agent unregistered, it means that that object doesn't know what's happening. It gets completely strange data and says, "Okay, I'm out of here. I don't know what's happening." And then I saw this. So it just crashed. So basically, it crashes the firmware. It crashes the entire service, because if you can see, it now shows the Bluetooth instead of device name, meaning that the connection has been disrupted. And actually, I haven't been able to restore the communication connection between those devices in 5-6 minutes. Now, since it was 4 years ago, and credit to Cypress and Broadcom, it has been fixed properly. So one would say, well, that's all fine. So what's the problem? But one thing is patching the code. Another thing is deploying it, and that's where things are getting very interesting. Usually, when one needs to upgrade the firmware, you need the usual process, which is pretty much secure and reliable one, is that you sign the compiled firmware with a private key, and then when you apply that update either over the air or through the debug ports or whatever, The firmware checks the signature, sees that, okay, it's all good. I apply the firmware, so I'll apply the update. If the signature is not matching, it says, I'm not going to update it. I'm just getting rid of. But the geniuses at Cypress and Broadcom decided to do things differently. Instead, what they do is they upload the firmware at the manufacturing stage in the read-only memory. The problem is it's read-only memory, so it means the firmware is getting immutable. So you can't update it further because obviously vulnerabilities may be, bugs may be, not necessarily security bugs. And so in that case, so instead they're using something called Patchram. So Patchrams are based on the flash patch units, which are part of the ARM architecture. So what they're doing is they have these fields. So these fields, so basically it overrides it overrides the certain elements of the memory by having the reference to the address and new values, and applies those new values. So basically in practice, so what happens? When the device, so basically these Patchrams are distributed as HTTP files for the devices, for example, on Linux. In Linux, you can find them in folder. I think it's user lib firmware brcm, and they're stored as HTTP files, and they're distributed as part of the repository, as a part of operating system repository in Linux. So what happens is when the device starts up, it loads the original firmware, which is stored in read-only memory. Then the operating system searches for the HTTP files, which are in this, which are either in this folder or in Android's case, for example, it may be a different folder. Then it extracts those fields, and it takes the memory address field. It checks the memory address, and then applies the value that is linked to that memory address value in this Patchram slot. The problem is you can't have, because there's a limited amount of those Patchram slots because the slot field is just 1 byte, so it means you can't have more than 256 slots. To make matters worse, Raspberry Pi 4 at least has only 128 slots. In phones, I believe it depends on the chip they're using, but it can be sometimes 192 or 200. So basically with the problem, what Cypress is doing is that they're adding those, and the problem is, Cypress, by 2019, when 1 year after Raspberry Pi 4 was released, it has, all of the Patchram slots were already reserved. Ironically, the date of the firmware compilation that was stored in read-only memory of the Cypress chip in Raspberry Pi, I remind you, this is immutable one. It was compiled in 2014. So it had to apply 5 years worth of fixes in only 128 slots. And so basically what happens is they are responsible for what exactly only they decide which bugs they need to fix, which security vulnerabilities they need to fix, and if the Patchram slots are running out, they have to replace them. So even if you, for example, you fix the Braktooth vulnerability, something else is unfixed, and you don't know what exactly is unfixed, and that is, so the moral of the story is that one thing to patch it, another thing to deploy it. It's not so bad though, because fortunately, in order to avoid this attack or any other against this chip, you can use Bluetooth external adapters. Now I've tested some of them. For example, I've tested TP-Link with Bluetooth 5. I think it costs 15-20 pounds on Amazon. It's been working well, but on the other hand, what I discovered is that first of all, the scanning range and range of that adapter is surprisingly less than on board the Raspberry Pi's Cypress on board chip. And secondly, Bluetooth, which is again I remind you, it's protocol stack for Linux. it's not always reliable working with with those devices. So you have to technically wait in whether you use Bluetooth or not. If you don't use Bluetooth, I suggest to shut down Bluetooth adapter entirely. If you use Bluetooth, either use the external adapters, or there is another option that I've seen recently, to use ESP32 microcontroller as a Bluetooth proxy, which is also doable. I think Home Assistant has some manuals for that. So two things left to talk. So first of all, to talk more about impact on devices. If you think to upgrade, or if you think that buying Raspberry Pi 5 will fix the problem, it won't. They use almost the exact same chip for Bluetooth and Wi-Fi, which is what Cypress chip is there for. But it does not concern Picos because they are different. They're completely different. It's essentially a microcontroller. Plus, Picos were released after Braktooth was publicly announced. So Picos are out of the scope for this attack. Other devices. So in terms of other devices, again, I haven't tested with other devices, but I know some people who have, and basically some of the recent iPhone models and Samsung Galaxy smartphones use that Broadcom chip, and they're vulnerable. So if you use one of those devices, just fair warning. Also, Braktooth is targeted. So basically, as I mentioned, so there are two Bluetooth protocols: classic Bluetooth and low energy. Low energy is mostly for dedicated for the so basically for communications where you don't need to constantly send messages, and also for example, for mesh networks. And Braktooth is targeted against exactly Bluetooth Classic. But there's a caveat though. A year before that, the same group of researchers released another group of vulnerabilities called Swaintooth, and this time it was targeted against Bluetooth Low Energy protocol stack implementations. Cypress and Broadcom chips have been vulnerable against only one, but it's actually the most severe one because it's a buffer overflow against link layer protocol. Link layer is basically link manager protocol, but for Bluetooth Low Energy. They have different implementations, but they serve the same purpose. So to conclude, if anyone wants to read read more in details about the vulnerability itself, or about the Cypress and Broadcom Patchram functionality, you can check some of these links. By the way, don't worry, I published the slides on my website. So again, and there will be a link at the end. So you're covered in that regard. Few words of thanks are in order. So first of all, I want to thank my employer for allowing me to give me a few days off to actually investigate this, and without being distracted by actual work. I want to thank also Vaibhav Bedi, who was one of the researchers of the Braktooth and with whom I've been keeping contact when I was doing those tests, and he essentially, and when I shared my findings, he said, yep, that's correct. Raspberry Pis are vulnerable. And also I want to thank Iska Klassen from Hasso-Plattner Institute, who previously she was working at CIMO Lab, because I've been sharing with the findings with her as well, and also her paper has been she was one of the authors of the paper that has been targeted against that describes the Patchram functionality, and also she's one of the best experts that I know in regards to Apple reverse engineering devices and the wireless communications. And finally, I want to thank each and every one of you for coming. I hope you enjoyed this talk, even though it's absolutely hot here. And yeah, if you want to check my website with socials and contact details, you can scan the QR code. And if you have any questions, I'll do my best to answer. Thank you.
we have any questions?
Yeah.
You say that the Raspberry Pi 5 is still effective, or is that recently come out?
Yes. So basically, the question is if Raspberry Pi 5 are still vulnerable. Yes, because for the Bluetooth, because Cypress chip in Raspberry Pis in all the revisions, like first, second, third, fourth, fifth, Cypress chip is being used for Bluetooth and Wi-Fi communications, and in Raspberry Pi 5 they're using the same chip. So yeah, it's still potentially vulnerable.
Any more questions? Lovely. In which case, another round of applause.